So I'll talk about, I'm giving a bit of an overview talk, or at least I'll try to. So I'll mention review of my work with Bensby and Brochet and with Brochet-Snyder. And then I'll spend much of the talk talking about some work in progress with Ian Lay, Gus Schrader, and Sasha Shapiro. So Schrader and Shapiro are among us today. Okay, so let's let G be a reductive algebraic group over C. And for now, let's consider S to be compact and oriented surface, possibly with boundary. So may or may not have a boundary. And so basic object of study is the character stack. So it's a moduli space of G local systems on the surface. So that is, for me, just representations from pi 1 of S in tori group G divided out by the conjugation action of G. And so I'll also use the notation, so the character variety is its affinization. So that means the character variety is an affine variety which I'll denote without an underline. And for that, what we do, well, when we build this thing as a stack, we write it as a quotient of a framed character variety by the G action. And so similarly, if I want to just study the affine quotient of this stack, then I take the framed character variety. I won't write it, but framed means that I trivialize at a single point, so that I choose a basis at a single point, and then that framed variety has an action of G. That's the one that I quotient by to get this stack quotient. And so if I just want to talk about functions and do linear algebra, then I just take the G invariance in the framed character variety. Okay, so so some basic, some context, I guess. Is so. Oops, I'm already.
Why don't you just take the G invariance? I'm a little confused. Why can you just not take the G invariance into functions and matching pi 1 of S into G?
Yeah, I mean, well, there's a global section. So yeah, so I'll mention this later, but there's global sections from functor from here. Oh, let me not write it. This is the stack quotient, and this is the affine quotient. So indeed, if I take the structure sheaf here and I take its global sections, then I'll get the same algebra. And this is just a way to present it. Yeah. So this is canonically Poisson. And so when S is closed, this is symplectic, and this is the sort of Atiyah bot and Goldman sort of independently defined this Poisson bracket. And there's more structure, which is if I have a 3 manifold, this is a Lagrangian. Correspondence in So it's a Lagrangian correspondence between the two symplectic structures on the boundary. So here the boundary I'm denoting as S plus union S minus for the incoming and outgoing boundary. So M3 is also oriented. Okay, so this is a very basic structure, and what we're interested in today is quantizations. Of the above. And what I want to try to convince you is that, so quantizations like this have been studied in quantum topology for a long time, but I think, I hope to convince you today that there's a lot of room for geometric representation theorists to get involved in studying these quantizations, and I'll try to pose some questions that are natural for us to think about. So there were three quantizations throughout the 90s and the early 2000s that were proposed for these sorts of things. So as far as I know, one of the first were what I've taken to calling AGS algebras, Alexeyev, Grossa, and Chomerus. And so these are certain generators and relations, algebras, and these really deform. What they really deform is this framed S when S has a boundary. Okay, so in a few more words, maybe I'll write over here. So if S has a boundary, then the framed character variety of S is just G to the 2G plus R minus 1 copies, mod G. So if you think about that, what I'm saying is that the pi 1 of a punctured surface is just a free group, and so all we have to do is spell out these elements of G mod G. Okay, and so what they really quantized was the was this space G. So these quantizations, there's some sort of Q algebra, quantum functions on G to the 2G plus R minus 1 that they defined using sort of well understood ideas from quantum groups, and that's our first point of contact. Another one was proposed by Turayev, and these are Skein algebras. So this is really in the case of SL2. And I'll talk a lot about this. Roughly, Skein algebras are sort of diagrammatical algebras that are defined by considering sort of all possible tangles on a given three-manifold modulo certain Skein relations like you see in the Jones polynomial. And then finally, what I want to spend a lot of time talking about today are the quantum cluster algebras of Fock and Gontreff. Okay. So, and so more recently, with David Ben-Zvi and Adrian Brochet, we gave a fourth construction in the language of factorization homology. And essentially, over the last few years, we've been just trying to pick off these classical constructions and understand how they fit in our framework of factorization homology. So, right. So what I want to spend the rest of the time doing is explaining this construction and recalling this construction in factorization homology, and then explaining how it is that it recaptures each of these quantization procedures. And I just want to emphasize that before this approach with factorization homology, it was there were a few sort of ad hoc constructions relating various of these different constructions, but it was essentially very difficult to relate these, and we'll see why. The relation through factorization homology is not direct. It's somewhat subtle.
Is there a statement that all of them are the same?
No, but we'll get there. They're all instances of factorization homology of different flavors, and I'll tell you those different flavors, and so using that you can make some precise relationships. That'll be the focus of today's talk. Okay, so for factorization homology, so we consider a certain two category called per, which is C linear locally presentable categories. Okay, so here locally presentable is a mild generalization of abelian. If you want to think about just abelian categories for the rest of the talk, that's fine. And so this is a two category, so those are the objects. We have co-limit preserving functors. And we have natural isomorphisms. Okay, so that's just the place where we're going to do linear algebra.
You want to assume the categories are co-complete?
That's what presentable means. Yeah, presentable means co-complete, so they're closed under all co-limits. And then we're going to fix a particular presentable category to be rep QG. So this is representation. So this is a braided tensor category of integrable representations for UQG. And so so here integrable just means, when Q is generic, for instance, integrable just means that they're locally finite dimensional. So they're direct sums of finite dimensional modules. And so the data of this as a braided tensor category, so the data of rep QG as a braided tensor category is equivalent to giving a functor from a certain category of disks, which I'll now explain, to presentable categories. And this category of disks has objects are just disjoint unions of D, so boldface D will denote just the two-dimensional disk, the two-dimensional open disk. The one morphisms are embeddings, so oriented embeddings. And the two morphisms are isotopies. Okay. So right, and so this has a symmetric monoidal structure just by disjoint union, and this has a symmetric monoidal structure on it, which is called the Deligne-Kelly tensor product. Okay. And this is just defined as you define tensor products of vector spaces by how you map out of it. So it's bilinear. So maps out of the tensor product are bilinear maps out of each component. Okay, so the first orienting observation is that the data of a braided tensor category is the same as the data of a functor from these disks to categories. So for instance, well, the disk itself, so D, that goes to the braided tensor category A. If I include two disks into a bigger disk, that goes to a functor from A tensor A to A. And because I have isotopies, I can say switch the order of these things. and that goes to the, so that isotopy goes to the braiding, etc. Okay, so this is some well understood correspondence. And so factorization homology, as defined by Ayala and Francis, is the universal extension from the category of disks to the category of surfaces. So this category of surfaces is defined in the same way, except I don't just restrict to disjoint unions of disks. I allow arbitrary things. And there's a canonical extension, which was defined by Ayala and Francis following a suggestion of Lurie. And I'm going to note that Z goes to ZQS. Okay, so it's an invariant of surfaces. It produces you a category, an abelian category. And we showed with Brochet and Snyder that this actually extends to a 3D TFT. Okay, so shortly after Ayala and Francis defined the factorization homology, Claudia Scheinbauer proved that it defines a two-dimensional TFT. So it's already giving us surface invariants of surfaces, and those actually fit into the framework of TFT. And we showed with Noah and Adrian that this is defines a three-dimensional TFT. So here to three manifolds, we assign vector spaces, and to surfaces, we assign this category ZQS. Okay, and so on down the line. So to one manifolds.
I would say that this is some piece of before the
Yeah, I'll remark on that. So this is a monoidal category, and this is a braided tensor category. Yeah, so the part that this data here defines a 2D TFT, this was in Claudia Scheinbauer's thesis. And so to answer Sasha's question,
specific example, I'm sorry, or some general result?
right, so because we're talking about the category of disks and we're talking about surface invariants, her statement is completely general. So any E2 algebra in any setting defines a two-dimensional TFT. And and what we showed with Noah and Adrian is that if you have a rigid braided tensor category, so rigid just means that it's generated by dualizable objects, then it defines a three-dimensional TFT. And just let me answer his question, and then I'll go to yours. So Sasha said we should think of this as a 4D TFT. That is how we think of it. So what we define is there's a certain 4 category, which is the Merida category of braided tensor categories, following Haugsang, Johnson, Fried, and Scheinbauer. So they tell us that there's a 4 category, and we take our braided tensor category and regard it as an object in that 4 category, and we ask how dualizable is it. And what we show is that if you're rigid, then you're 3 dualizable, so you define 3 manifold invariants. But in order to be 4 dualizable, you need something stronger, something like modular or at least braided fusion to get to 4 dualizability. So the point is the vector spaces make sense and converge, but the numerical invariants to 4 manifolds don't make sense. If they do, when they do, so if we restrict to really small categories, then we do get numbers. And this was what was called the Crane-Yetter Kaufman. No, I mean these ones have like finitely many simple objects. RepQG has infinitely many simples.
And so when you say surfaces, you mean surfaces with boundary, right? Or
they may or may not have boundary.
but then I'm a little bit confused. So why do you assign same kind of object to?
Here, well, for a TFT, this is what I'm assigning to a closed surface. and as one expects. Yeah.
So, how computable is it? Like, for example, for Briscoe 3 manifolds,
I'll-
can you compute?
I'll talk about computations right now. Yeah, that's what we're going to spend the day doing, is computing some examples. Yeah.
Do you see into one of the all of that? You need to move to infinity categories?
Say again. Sorry.
You need to move to infinity categories for any of those statements?
Well, in the definition, like in the constructions of Ayala Francis, they're working with infinity categories. So presentable, this is a 2, 1 category, which one can trivially regard as an infinity 1 category. But all the colimits that we ever compute are just computed in 2 categorical terms.
So you can do the whole thing in 2 categorical terms?
Yes, absolutely. Yeah. I mean, the only catch to that is the computations are always done in 2 categorical terms. There's a 4 category of braided tensor categories. And so, you know, when we talk about the notion of bimodules, for instance, it's the sort of 4 categorical notion. But the computations themselves always are just linear algebra. Yeah.
So the uniqueness statement is really for the infinity categories, but do not have the uniqueness statement for the 2-1 category, or it's just...
Maybe let's discuss that kind of question later, if that's okay. Yeah, it's a good question, but you mean this uniqueness?
Yeah,
It's a unique. It's a canonical extension. It's a left con extension. This is a generating subcategory, and it satisfies a certain defining universal property. Yes, you simply regard the 2-1 category as an infinity 1 category with discrete higher morphism spaces. Yeah, yeah. So it's yeah. Okay, so. Yes. So the miracle of the factorization homology construction is that it is computable, and actually, let me just say now, for surfaces, I'm going to use over and over a property called excision that was proved by Ayala and Francis. And excision says that if I want to compute these invariants for some surface, if I present my surface as glued out of 2 smaller surfaces over some interval, then I get an equivalence of categories between, I can compute the surface, I can compute the invariant of the first surface, I can compute the invariant of the second surface, and those are both module categories over the cylinder. And I take the relative tensor product. So this is an instance you're asking about with boundaries. So I'm saying this is a module for that monoidal category, this is a module for that monoidal category, and I just compose them as modules, which is I take the relative tensor product. Okay, so this is what allows us to do computations, as you'll see as we go along. So using this property, we did some computations.
Sorry, but I'm still a little confused. So you're assigning a category to every surface with boundary.
No, you're assigning a category to every surface, full stop, with or without boundary.
With or without boundary.
With
So
or
you've got
without
the
boundary.
Surface with boundary, surface without boundary, you associate the same kind of thing.
That's right, yes, that's right.
Which is kind of surprising from a TFT point of view.
No, it's not.
When you have a boundary, it also carries an action of a monoidal category associated
Oh, I
with
see.
that.
Okay.
Right, exactly. So if you like, we're assigning not just a category, but a module category over its boundary. So that's the beautiful thing about factorization homology, is that everything is based in categories. Okay, so Sasha is interested in the monoidal category to a surface, what the monoidal structure is on 1 manifolds. And so this is the monoidal category of modules over a certain algebra. This is called the reflection equation algebra associated to OQG. And the buzzword for today is that these are the Q Harish-Chandra bimodules. No, that's a good question. So the question is, are there assumptions on Q? No. So that was an important point. So Q can be generic, or Q can be a root of unity. In the root of unity case, you need to say what you mean, and Pavel Safronov will say that very precisely. If Q is generic, the behavior is, of course, different, but the theorems I'm stating on this board apply equally well. So Q Harish-Chandra bimodules. So this algebra OQG has a certain degeneration which recovers the universal enveloping algebra of G. It's a bit surprising because it has another degeneration which recovers functions on the group G. But because it's non-commutative, it really behaves the most like the universal enveloping algebra, but may be valued in the group rather than the Lie algebra. Okay? And so if we would study equivariant U of G modules, but which are not finite, then that would be the notion of Harish-Chandra bimodules. And likewise, so this monoidal category is, it carries a structure which resembles Harish-Chandra bimodules. I think Sam will talk a bit about this, if I understand right. So that's the first one.
This is the same category I used to sometimes write OQG over G mod.
You could write it that way. Yeah, that's a good point. So, right, thank you. So this is for S1. So the character variety for S1 would just be G mod G, G quotiented by its adjoint action, because pi 1 is just Z. So we have a single group element, and we regard it up to conjugation. So note so Sasha asked, does this apply to any Q? These statements apply literally to Q equals 1, the same. So if I plug in Q equals 1, then I just get O of G modules in rep G, which is to say I get equivariant quasi-coherent sheaves on the stack G mod G. So it's exactly a quantization in that sense. Okay, to a punctured torus, we get another nice algebra. We get modules for another algebra, which is dqg, and these are some q difference modules. On G. And so if we send Q to 1 in this way that we got U of G, then this becomes differential operators on G. So this algebra Q deforms the algebra of differential operators. And then the most interesting of all, so these are what you would call weakly equivariant modules. They're DQG modules, and they have a compatible action of the quantum group, which is integrable, but they're what's called weakly equivariant. And I'll say now what strongly equivariant ones are. And these are what I'm calling, what we're calling Q character sheaves. Okay, so this notion of strongly equivariant means that, so there's a moment map from OQG to DQG, which recovers the inclusion of vector fields from U of G to D of G when we do this degeneration. But in topological terms, it just comes from the fact that if I have a torus with boundary, then it has a boundary. And so I get an inclusion of the boundary circle as the boundary. And it turns out that this induces a homomorphism of algebras from OQ, which is assigned to the circle, to DQ. Okay. And so strongly equivariant means that there's a compatibility between. Now, what happens is we get sort of two actions of the this algebra OQG. So there's something called the Rosso isomorphism, which tells us that OQG sits inside of UQG as a subalgebra. And so now strongly equivariant means that there's now two actions of OQG that I insist coincide. So on the one hand, I was looking at modules for repQG. I was looking at modules which are equivariant for UQG, so I've already fixed the structure there. And on the other hand, I have this homomorphism from UQ, so I get another one. And I ask that those two coincide, and that defines the notion of a strongly equivariant module. And what we prove is that that the thing you assign to the 2 torus is this category of strongly equivariant modules. It's actually, it turns out it's a full subcategory of the punctured torus. So I get two actions of this OQG. One is by taking the module, forgetting repQG, forgetting the equivariant structure, and just pulling back to OQG. And the other is by forgetting the DQ structure and just regarding it as a UQG module. And I ask that those coincide. And of course, that just mimics the notion of strongly equivariant D modules that you're used to.
And so, sorry, this embedding from OQG to DQG doesn't it extend to the embedding from UQG to DQG?
There is not an embed. No, the DQG that I use here does not have an embedding of UQG.
So I mean, because this embedding here, I mean, this embedding from OQG to UQG, it's it's not an isomorphism, but it's very close to being an isomorphism.
It's very close to being an isomorphism. So yeah, so there's a certain element which, if I localize it, then I can extend it. But that element is not localized here, and that's actually quite important, because, for instance, classically what you're doing is you're throwing away some locus, which is the degeneracy locus of your Poisson bracket. So it's a nice thing to do, but if you do that, then you lose. I mean, you lose important parts of the variety. Yeah. Okay. So.
I'm sorry, when you forget this, you forget this DQG, you get a UQG structure, and then you restrict the OQG by the vector map.
That's right. That's right. And you ask that those two different actions of OQG be compatible. So it's not at all obvious that that's the right definition. That's part of the content of this theorem, but that turns out to be the right thing to do.
Structure, does it extend to a DQG localized structure?
No.
Because the OQG inside extends.
Let's discuss this after well, okay. I have DQG. I have a module over it. I can restrict it, and I get a module for OQG. Okay. That's M1. On the same underlying vector space, I have an a priori integrable UQG structure, and I can just restrict that through this homomorphism from UQG to OQG, and I ask that those two actions of OQG coincide.
I did understand that.
Yeah.
I'm
Okay.
just saying because this OQG extends inside DQG.
It does not. It does not. So there is not a homomorphism from UQG.
No, that's not true, but the subalgebra extends to the UQG structure. So you had said before that UQG embeds into a localization of UQG. So it would seem to indicate.
What Fred is saying is that there's a slightly bigger algebra acting, because there's an action of DQG, and in addition there's an action of UQG. So altogether they form a bigger algebra, which is
Yes, that is true. The support of the strongly equivariant modules are automatically in this localization that you've suggested. Yeah, that's right. That's right. Actually, that is useful in some constructions. Thank you. Okay, so right. So I think so one thing that tells us is that it's interesting to study these. There's also an analog of this for higher genus. I'm just focusing on genus 1. It's useful to study these categories by using our intuition of character sheaves, and so that's, I think, what Sam will discuss in the next talk.
It's easy to see in what sense this is the quantization of the Poisson bracket you mentioned before.
Yes, it is. For instance, so DQG is. I should have said this. So D.
Well,
so
I mean, here when you have this explicit description, I can understand. But so for general surface, we don't describe
general
it as a-
punctured surface or closed surface.
Either one. I mean,
So for okay,
get
so
a category, and in what sense does it quantize the crystalline variety?
Right. So for a general punctured surface, the algebra that we get is isomorphic to the Alexeyev-Grosse-Schomerus algebra, and this is known to degenerate precisely to the Fock-Rossley-Poisson bracket on the character variety. So it's as strong as you could hope for. For closed surfaces, it's a reasonable question. You have a category and not an algebra, right? These examples might lead you to believe that it's always modules for some algebra, and that's not a priori true. For some groups it will be true, but for some groups and for some surfaces it won't. So Sam will talk about this. Yeah, the sense in which it's a quantization in the category sense, I think maybe it's an interesting question. Yeah.
What's the ZQ of a disk?
Oh yes, of course. Sorry, that was very important. Yes. So by definition, we extended from the disk category here. So by definition, ZQ of the disk is the category rep QG. Yeah, thank you for that question. So, and what we're saying is that the rep QG is a quantization of rep G, and rep G would be would be QC of point mod G. So that's we're taking that as our basic intuition, and we're extending that to surfaces. Yeah, thank you. Okay, and so all these computations in that theorem, they all boil down to just computing excision in categories, and you have lots of tools for doing that. Okay, so that's the relation to the AGS algebras. Okay, so yeah, these algebras are mostly how I think about these categories, but for applications, it's nice to note that they have a connection to Skeins. So I'm going to fix G to be SL2, and I want to recall what Skein modules are. So recall that the Jones polynomial is determined by what's called a Skein relation. Okay, and so the Skein relation on the Jones polynomial says that if I have a crossing in some projection, I can resolve that in terms of the Jones polynomial of different ways to alleviate the crossing, and I get these factors q to the 1/2 and q to the -1/2 that appear here. Okay, so Kaufman and Turayev suggested a generalization of the Jones polynomial, which is called the Skein module. And so we have a three-manifold, let's say oriented and closed. Three-manifold. And so the Skein module of the three-manifold is just a vector space, despite this word module. And what we do is we take the span of all links in our three-manifold, mod, isotopy, of course, and also the Skein relations. So because we have an orientation, it makes sense, it allows us to make sense of this idea of knot projections. And so we say if there's any ball in your three-manifold where the different knots look like these three configurations, then you impose that relation. So this defines you some vector space. So despite the easy definition, these are impossible to compute. They're essentially impossible to compute. So an open question is, are they, given a given three-manifold, is it zero-dimensional? Is it one-dimensional? Is it infinite-dimensional? You just, with these relations, you don't have very many tools, except you need to really understand your particular three-manifold and do some sort of combinatorics. Yeah, that's on the paper. That's a good question. So for the three-sphere, this is C. And you knew that when you were an undergraduate and you took your first knot theory course, because the fact that this is C is what tells you that the Jones polynomial is well defined. Because I can take any link and I can use these relations and write it as a multiple of the unknot or several unknots. And so then I get C. Yeah, thank you. Yeah, so there's of course a version for both, but let's say that I work over rational functions in Q, or Q is generic. Yeah, thank you. Yeah. The Jones polynomial will of course always give you Laurent polynomial, but okay. Right, and so yeah, very little is known about these for any general class of three manifolds, and so it's a challenge to understand those. And traditionally, people have studied these by Skein algebras. So if S is a surface, I'll also denote by the same notation SQ of S to be the Skein module of the surface cross an interval. But now this has an algebra structure because I can stack links on top of each other in the interval direction. Okay, so this is an algebra. This is called the Skein algebra. Okay, and so when you have a manifold with boundary, then you get an action of the Skein algebra on the Skein module just by sort of putting the things into the boundary, pushing them into the boundary. And this looks a lot like a TFT, but it's not. It fails to be a TFT for a good reason, which is that you need to do a little bit better. And so
when you define this Skein modules, then do you really consider links, or do you consider things which can sort of end on the boundary?
That's what I'm going to say now. Yeah, so right here, this has nothing ending on the boundary. And so the three manifolds also have nothing ending on the boundary. And so all I'm doing is inserting just links in. And what you're saying is that's a bad idea, and I'll now say I agree. So there's something called the Skein category. So I'll write that as, okay, so this is a category. So this was essentially proposed by, let's say, Morrison and Walker, and let me also mention Johnson-Fried. So Morrison and Walker, at least were thinking about this following definition when they introduced blob homology, which preceded factorization homology by many years. And so what they said is that we should study a category just like Sasha says. So objects are finite sets X inside a surface. And morphisms are skeins starting and ending at X and Y. Okay, so so here's my surface across the interval. And before I was only allowing, even though I was considering surface cross an interval, I was never allowed to come near that boundary surface. But now we say, okay, I fix a finite set of points here and another finite set of points here, and a morphism is sort of anything I can draw that connects those as a tangle.
You mean skeins in S cross an interval?
Yes, Skein.
No, I mean just when you wrote so it's in a home from X to Y.
Skeins in S cross, yes, sorry. Skeins in S cross I. So that's the notion of the Skein category. Okay. Notice that this is not the kind of thing we like to study in representation theory. It's not abelian. So I have objects like this, I have morphisms like this, but I certainly can't construct kernels or co-kernels. That won't be another such object. Okay. Theorem, nevertheless, of my PhD student Juliette Cook sort of following ideas of Johnson-Fried and Kevin Walker. So Theo has a sort of unpublished notes where he suggests that the following should be true. He essentially conjectures it. He states it without proof. And he sort of attributes the main ideas to Kevin Walker. Is the following. So let me say it this way. So if we map from disks not to presentable categories, but to idempotent complete or Cauchy complete categories. So these are sort of small k-linear categories. Then again, a braided tensor category, semi-simple. A semi-simple braided tensor category determines us a functor like this. And we can just as well define the factorization homology in the same way. And the claim is that this is exactly the Skein category of S. Okay, so Skeins arise not as these co-limits in presentable categories, but in this world of small categories. Okay, but this is only true then for Q generic. So this precise statement only applies for Q generic. Yeah, exactly. So for instance, for rep QSL2, then we basically, what we're saying is that, so I've simplified to SL2 just to reduce the notation. But what you would say is that you're not allowed to mark these points X by arbitrary objects of your category. Each X has to be marked with the defining representation of SL2. And so if I have 3 dots, then that has to be sent to X tensor V tensor V tensor V, where V is the defining representation. So for a general semi-simple tensor category, you can mark each dot by a different symbol, and this is enough. But in the SL2 case, you can get away with just the defining representation.
So is theory good for any G, or is it
her theorem is true for any G or any braided tensor category which is semi-simple, where you just restrict to the simple objects, and then you regard it as a functor from disks to ICO.
You recover the Skein category?
You recover the Skein category. That's the content of her theorem. Yeah. And so, as I say, this was stated without proof in some notes of Johnson-Fried, and well. Okay, Kevin Walker made similar statements about blob homology, but before factorization homology was a thing, and there were technical difficulties in actually proving that, but they've since been addressed. Yeah, Sasha?
Can you say once again what's
ICO, so these are idempotent complete k-linear categories. So that just means if I have a morphism, I can't necessarily take its kernel, but if that morphism is idempotent, then I can project, and therefore I get both its kernel and its co-kernel, but so that's only well behaved in the semi-simple case. Okay, and so a corollary of this theorem is that if I take these categories here for some surface, and I look at their compact projective objects, then that subcategory is equivalent to the Skein category.
Is this just for Q generic?
This is also for Q generic. That's an important point. Thank you. And in fact, there's just some 2 functors between ICO and per. If I have an idempotent complete category, there's a free co-completion that turns it into presentable category, and I can take compact projectives. Those are adjoint functors, and that's essentially how you prove it from this identity to this identity. You just have an adjunction.
Do you expect this corollary to be true, though, at roots of unity?
Yeah, so let me talk about what is and is not true at roots of unity. So this corollary is definitely false. It's super false when q to the L equals 1. And the reason is that basically I mentioned that the way that you prove this is using an adjunction. And so if I have a, so basically I can express, so the idea is I can express homs in ZQS in terms of homs in rep QG. For instance, if I have some surface with or without boundary, I can always choose a disk in there, and I can include that disk, and I get a functor from rep QG to ZQS. And it turns out that for the objects that come from this, for these Skein objects, they just come from including into a disk. And then if I want to ask, is that projective or not, I can just take whatever object I was trying to hom with, forget it down to rep QG, and then I can just take homs in rep QG. And so the point is that if you're not semi-simple, then the corresponding Skein objects that you would, the objects you would get, you would always get a functor this way, and they're not projective. Simply because if you're not semi-simple, you weren't even projective in rep QG, so you have no chance to be projective there. So this corollary can't be true when Q is a root of unity. However, so some work in progress. Again with, so a new paper with Adrian and Noah Snyder is to define certain tilting subcategories. So that is, I can nevertheless look at the subcategories which come from tilting modules, and those categories won't be the compact projectives, but their homs will still be computed via Skeins. So that is to say that there's a tilting subcategory. So we have ZQ of S. It has a certain tilting subcategory inside here, and homs in here in the tilting subcategory are given by Skeins. So sort of what it's saying is that this category, its compact projectives, its structure as a category is not the same as tilting modules, but there's a subcategory of tilting modules who behave just like Skein modules. Okay, and that sort of pattern goes back to the very definition of Skein modules, the way they're defined. Sorry, the way tilting modules are defined. Like for instance, for SL2, you just define the tilting modules to be: I take tensor products of V, and I take all of the idempotents, and I just project those. So at a disk, this is a true claim, and then I claim that we can export that to general surfaces. So that motivates some of the work we did with Jordan and Pavel. Yeah?
For this, it's already in the work of Harish-Chandra that's his recent work, in some sense.
Yeah, oh yeah, well, I wouldn't attribute it
The fact that you can compute it in terms of means that you have this construction, this combinatorial description of that category.
Yeah, in the quantum setting, I attribute this to like Anderson, Henning Anderson, and people in. Yeah, exactly. Yeah, yeah, indeed. For on the level of a disk, this is well understood, and the game is to sort of export that to general surfaces. Yeah, yeah. So yeah, there's a well understood theory of tilting modules for the disk, and we want to just export it. That's right.
Sorry, I have a technical question. So did you say what is the definition of Skein category for a surface with boundary?
Yeah, it's always the same. It's just this. It's whether or not you have boundary.
For a disk, I mean, you had this kind of dramatic definition of what Skeins were, and so if you
even if you have boundary, the same definition. You just cross with the interval.
But you just kind of ignore the boundary of the surface.
Yeah, it doesn't enter into the definition. There will be extra structure because of it.
Still, but you don't have to do anything dramatic on the boundary.
Okay. So I have 5 minutes to finish the last half of my talk. So that's okay. That's my fault. I had too much that I tried to do. Let me just at least state the main results of the work with... So I apologize if this is a bit rushed. I was a bit telegraphic because there will be 2 more talks that expand on each of these other themes. But I want to spend the last 5 minutes doing the part that won't be in either of the other 2 talks. So we talked about Q character sheaves, and we talked about Skeins. And so I want to talk now about quantum cluster algebras. Of Factorization. Okay, so what they do is they quantize local systems, a moduli space of local systems. To deal with this, with some of the problems with the stack with the character variety stack, they fix additional data that sort of frees up the action. So they consider what I'll call a flagged surface. So apologies to Gus and Sasha because this doesn't match our draft. So this has punctures and it has boundaries, mark points. And these always lie in the boundary of S. So for Factorization, you always have a boundary. And so, for instance, here's the disk. It has 2 marked points on the boundary, and it has 1 puncture. So these are the marked points, and this is called the puncture. Okay, and I prefer to write a topologically equivalent picture here, which is we grow each of these points into little regions, and then I write G here, T here, and I write B on all of the one-dimensional defects. Okay, and then there's a flagged local system. So is 3 pieces of data. So a G local system on the bulk, the part labeled by G, a reduction to the Borel on SB, and a T framing. Okay, so just to give you some examples, for instance, if we would just do a disk with a bunch of marked points, well, then there is no interesting local system, so we just get a choice of flags, G mod n cross G mod n, but we have to regard this modulo the diagonal G action, which changes the G framing, and the T to the N action, where we have N marked points. Okay, and I'm running essentially out of time. So let me just say that, right, so there's a category of flagged disks. So this is generated just by a disk labeled G, a disk labeled H or T, and a disk labeled B. Okay, and it's defined in a similar spirit to before, and this sits inside a category of flagged surfaces, and the data of a functor from this thing to presentable categories is the data that sends this to rep QG, this to rep QT, and this to rep QB. So that's already a non-obvious statement. I'm saying that this category that has generated by these disks, that I can represent it by these classical objects. And then we define the invariant of flagged surfaces to be the unique extension, and now this exists by Ayala, Francis, and Tanaka. So this is the theory of stratified factorization homology. And let me just state it in the SL2 case. The higher, at least for SLN, it's just more combinatorial stuff to state it, which is, sorry, before I state that, I need to say one more thing, which is what Fock and Guntroff actually do is, given S and given a triangulation, they construct an open set inside this space of local systems. And this open set they show is isomorphic to just a big torus. But it depends on a triangulation that they have to choose. And they show that any two triangles are birational. So these open sets that you get are a bunch of tori. They're all birational to one another, and they have a globally defined Poisson bracket. So Fock and Guntroff quantize this Poisson bracket, and the point for them is it's very easy to do because this is log canonical Poisson bracket, so it has an obvious quantization in the obvious way. So they've done already the hard work by finding these open sets. And so what we show with Lay, Schrader, and Shapiro, and I'll close with this. Okay, so for every S and every triangulation, remember here, for safety's sake, G is SL2, we have a subcategory, localizing subcategory, and this has a distinguished object in it, which is like the structure sheaf. And the endomorphism algebra, it's a generator, it's a distinguished generator of that subcategory, and its endomorphism algebra is isomorphic to a quantum torus in variables equal to the number of edges of your triangulation, and this is the same as Fock and Guntroff. Okay, so the point is that we recover what they defined by generators and relations, the system of birational non-commutative tori, and we rather define a category once and for all, and we show that this sort of non-commutative stack has open charts whose coordinate algebras are the quantum tori that they've defined. And the point of the paper is to rediscover their combinatorics, which I never understood. So the amalgamation, mutation, et cetera, that you do in Fock-Guntroff coordinates, they all just follow when you read the factorization homology manual. I'll stop there. Thanks.